Welcome, dear friends, to another serene exploration with Earth with nature. I'm so glad you've joined me for this gentle journey into the heart of the cosmos, where we'll unravel one of the universe's deepest mysteries. Why did matter triumph over antimatter, allowing galaxies, stars, and life itself to bloom? Picture yourself nestled under a vast starlit sky, the cool night air brushing against your skin, as we embark on a calming voyage through the hidden rules of symmetry and the quiet mathematics that shape all existence. Let's set aside the rush of daily life, breathe deeply, and allow our minds to wander across billions of years and light years, contemplating the delicate balance that birthed our reality. This isn't just a story of physics. It's a tale of beauty, imperfection, and wonder, a cosmic dance of forces and particles that somehow led to you and me. As we settle into this soothing narrative, imagine the universe as a grand tapestry, woven with threads of order and chaos, symmetry and its subtle breaks, each stitch a clue to why we're here. We'll explore the elegance of nature's patterns, the profound insights of Emmy Noether's theorem tying symmetry to conservation laws, and the peculiar ways the cosmos defies its own rules to favor matter over its mirror twin, antimatter. Along the way, we'll drift through the early universe's fiery infancy, ponder the mystery of baryogenesis, and gaze into modern science's quest for hidden truths through neutrinos, gravitational waves, and particle colliders. This is a space for reflection, a place to marvel at our fragile yet awe-inspiring place in the grand scheme. So, find a cozy spot, perhaps with a warm drink in hand, and let's begin this contemplative journey into cosmic wonder. Pause for a moment. Can you feel the quiet hum of the universe calling to you, inviting you to listen to its ancient story? Let's dive into the concept of symmetry, a principle that echoes through nature, art, and physics alike. Symmetry is everywhere. Think of the perfect spiral of a seashell, the mirrored wings of a butterfly, or the balanced arches of ancient architecture. In physics, symmetry isn't just beauty. It's a fundamental law, a guiding light that shapes how particles and forces interact. It's the idea that some things remain unchanged even when transformed. Rotate a circle, and it looks the same. Flip a snowflake, and its pattern holds. But beyond aesthetics, symmetry in the universe dictates profound truths, as we'll see through the lens of one of history's most brilliant minds, Emmy Noether, whose 1918 theorem revealed a breathtaking connection. For every symmetry in nature, there exists a conservation law. Time symmetry gives us the conservation of energy. Space symmetry ensures momentum is preserved. This elegant insight, born from pure mathematics, underpins why the universe behaves as it does, from the orbit of planets to the flicker of a candle. As we linger on this thought, imagine the cosmos as a vast symphony, each note of symmetry preserving the harmony of existence. Yet, as we'll soon discover, the universe isn't a perfect mirror. It breaks its own rules in subtle, life-giving ways. Let's ponder this for a moment. How does the idea of universal balance resonate with you, knowing that even the stars obey these unseen patterns? We'll build on this as we journey deeper, connecting symmetry to the very fabric of reality, and ultimately to why matter, the stuff of us, emerged victorious in a battle against its shadowy counterpart. This exploration ties into broader wonders, like the search for other worlds, exoplanet mysteries that hint Earth may be one of many in this symmetrical yet broken cosmos. So, let's glide forward, carried by curiosity and the soft rhythm of discovery, into the heart of physics and the story of creation itself, marveling at planetary science facts that ground us in this vast, interconnected universe. As we drift further into our calming cosmic journey with Earth with nature, let's immerse ourselves in the strange and beautiful phenomenon of symmetry breaking, a quiet rebellion in the universe's rulebook that made life possible. Picture the early cosmos, a mere whisper after the Big Bang, a sea of pure energy where all forces and particles were unified in perfect symmetry, like a flawless crystal sphere shimmering with potential. But as the universe cooled, this symmetry began to fracture, much like ice forming intricate, unique patterns on a frozen lake. One of the most profound breaks occurred in the weak nuclear force, one of the four fundamental forces alongside gravity, electromagnetism, and the strong force. Unlike its counterparts, the weak force, which governs processes like radioactive decay, doesn't respect a symmetry called parity, meaning it behaves differently in a mirror world. Imagine holding up a mirror to reality. Most forces wouldn't care, acting the same, but the weak force does, showing a preference for handedness, a bias discovered in 1956 by physicist Chien-Shiung Wu in a groundbreaking experiment with cobalt-60 atoms. Her work revealed that beta decay particles spin in a preferred direction, shattering the notion that nature is always impartial. This subtle imperfection, this tiny crack in the mirror of symmetry, is a cornerstone of why matter won over antimatter. In the universe's infancy, matter and antimatter, perfect opposites that annihilate each other on contact, should have been created in equal amounts, canceling out to leave nothing but light. Yet here we are, made of matter, surrounded by a cosmos of matter. Why? Scientists believe this asymmetry in the weak force, among other processes, tipped the scales, allowing a sliver of matter, perhaps one particle in a billion, to survive the annihilation. This is part of a process called baryogenesis, a mystery we'll explore soon, but for now, let's sit with the wonder of this imbalance. Close your eyes for a moment and imagine the universe as a vast potter's wheel, spinning with perfect symmetry at first, then wobbling just enough to shape the clay of reality into something unique, us. Doesn't it feel extraordinary to think that a flaw in nature's design is why stars burn, why planets form, why life breathes? This connects to our broader cosmic wonder, as we ponder Earth's place among potential exoplanet mysteries, worlds that, like ours, may owe their existence to these ancient, broken symmetries. Let's reflect on technology's role here. Experiments at facilities like CERN, home to the Large Hadron Collider since 2008, smash particles at near-light speeds, recreating conditions of the early universe to study these asymmetries, seeking answers in collisions that release energies up to 13 trillion electron volts. Each discovery, like the 2012 Higgs boson detection, adds a piece to the puzzle of why matter persists. As we linger on this thought, consider how the universe's imperfections mirror our own. Aren't we, too, shaped by flaws that make us unique? Let's transition now to a deeper look at the early universe's story, where symmetry and its breaking unfolded over cosmic epochs, leading to the formation of everything we know, from the smallest atom to the grandest galaxy. This journey ties into planetary science facts, reminding us that Earth, orbiting a G-type star at 149.6 million kilometers, is a product of these ancient imbalances, a fragile gem in a universe that could have been empty. So, let's continue our gentle exploration, carried by the soft current of curiosity, into the dawn of time itself, marveling at how a broken rule became the seed of creation. Welcome back, friends, to this tranquil odyssey with Earth with nature. Let's now journey to the very beginning, to the first fleeting moments after the Big Bang, where the universe was a cauldron of unimaginable heat and density, a realm of perfect unity. Imagine it, a singularity smaller than an atom, hotter than 1,000,000,000,000 suns, where space and time themselves were born 13.8 billion years ago. In this primordial state, all forces, gravity, electromagnetism, the strong and weak nuclear forces, were one, merged in a flawless symmetry, like a single boundless ocean before it splits into rivers. But as the universe expanded and cooled in fractions of a second, this unity began to unravel through phase transitions. Much like water freezing into ice, each shift breaking symmetry and giving rise to the distinct forces and particles we know today. One pivotal moment was cosmic inflation, a rapid expansion just 10 to the power of -36 seconds after the Big Bang, stretching the universe by a factor of 10 to the power of 26 in a blink, smoothing out irregularities and setting the stage for matter to form. Picture this expansion as a balloon inflating so fast that any wrinkles vanish, creating a vast, nearly flat canvas for reality to paint upon. During these early epochs, particles and antiparticles danced in a deadly waltz, annihilating each other into bursts of light, yet, as we've touched on, a tiny asymmetry, perhaps driven by the weak force or other unknown processes, allowed a whisper of matter to endure. This era, studied through relics like the Cosmic Microwave Background (CMB), a 2.725 Kelvin glow mapped by satellites like Planck from 2009 to 2013, offers a snapshot of the universe at 380,000 years old, revealing the seeds of galaxies in its faint temperature fluctuations. Let's pause and breathe in this wonder. Isn't it humbling to think that the light we detect today, stretching across billions of light years, carries whispers of those first moments, of the symmetry that broke to birth our world? This story ties into exoplanet mysteries, as the matter that survived shaped not just Earth but countless other worlds. Over 5,000 exoplanets confirmed by missions like Kepler and TESS by 2023, orbiting distant stars, each a potential echo of our own cosmic origin. Modern technology like the James Webb Space Telescope launched in 2021 peers into these ancient times by capturing light from galaxies formed just hundreds of millions of years after the Big Bang, helping us trace how matter clumped into stars and planets. Reflect for a moment. Does knowing our universe emerged from such a delicate shift make Earth feel more precious, more rare? As we ponder this, let's glide toward the enigma of baryogenesis, the process that ensured matter's survival, connecting these early transitions to the broader implications of why life exists at all. This narrative weaves into planetary science facts, grounding us in the reality that Earth, with its 71% ocean-covered surface, is a direct descendant of those first, fleeting asymmetries. So, let's drift onward, wrapped in the soft glow of discovery, exploring how a sliver of matter defied the odds to build the cosmos we call home, and what that means for our search for other habitable worlds in this vast, wondrous expanse. As we continue our peaceful exploration with Earth with nature, let's settle into the profound mystery of baryogenesis, the process that tipped the cosmic scales, ensuring a sliver of matter survived the annihilation with antimatter to form everything we see. Imagine the universe in its first seconds, a turbulent soup of energy where matter and antimatter particles popped into existence in near-perfect balance, each pair destined to collide and vanish into light. Theory suggests they should have been equal, leaving nothing behind, yet here we are. Stars shine, galaxies swirl, and life thrives on a blue-green world called Earth. How did this happen? Baryogenesis, a term combining baryon, particles like protons and neutrons, and genesis, creation, describes the unknown mechanism that created a tiny excess of matter, perhaps one extra baryon for every billion antimatter particles, enough to build the cosmos after the rest annihilated. Scientists proposed three conditions for this, outlined by physicist Andrei Sakharov in 1967. A violation of symmetry, like in the weak force, a departure from thermal equilibrium, as during cosmic phase transitions, and processes that break baryon number conservation. While we've seen hints of these in lab experiments, the full picture remains elusive, a puzzle studied through cosmic relics like the CMB, which constrains the baryon-to-photon ratio to a mere 6.1 times 10 to the power of -10, a testament to how little survived. Picture this imbalance as a single grain of sand on a vast beach. Yet that grain grew into mountains, oceans, and us. Isn't it astonishing to think that such a minuscule difference shaped all of reality? This mystery ties into our cosmic wonder, as we reflect on Earth's rarity among potential worlds. Exoplanet mysteries probed by missions like the European Space Agency's Ariel, set to launch in 2029, which will study distant atmospheres for signs of life, echoing the same matter-driven story. Technology plays a vital role here. Particle accelerators like CERN's LHC recreate early universe conditions, searching for new particles or forces that might explain baryogenesis, while neutrino experiments, such as the Deep Underground Neutrino Experiment, DUNE, starting in the late 2020s, probe if these ghostly particles hold clues to symmetry breaking. Pause and let this sink in. Could the answer to why we exist lie in a particle so elusive it passes through us unnoticed? As we marvel at this, let's transition to modern science's quest for hidden rules, connecting baryogenesis to broader questions of cosmic balance and our place among the stars. This links to planetary science facts, reminding us that Earth, formed 4.5 billion years ago from matter's victory, hosts life in a universe that could have been empty. So let's flow gently onward, cradled by the rhythm of these ancient truths, exploring how today's experiments, from gravitational wave detectors to colliders, seek the laws that shaped our existence, inspiring us to cherish this fragile matter-made world amid the vastness of space. Let's now turn our gaze to the cutting-edge frontiers of science, where humanity seeks the hidden rules of symmetry and asymmetry that govern the universe, using tools of incredible precision to uncover why matter triumphed and what deeper balances await discovery. Imagine standing at the edge of knowledge, peering into the unknown with instruments like the Laser Interferometer Gravitational Wave Observatory, LIGO, which since 2015 has detected over 90 ripples in spacetime from merging black holes and neutron stars, offering a new way to test cosmic laws. These gravitational waves, traveling at light speed of 299,792 kilometers per second, carry echoes of violent events, potentially revealing if symmetry-breaking processes in the early universe left detectable imprints. Meanwhile, neutrino experiments like Japan's Super Kamiokande, operational since 1996, study these nearly massless particles that oscillate between types, hinting at symmetry violations that might explain baryogenesis. Picture neutrinos as cosmic messengers, billions passing through you each second, holding secrets of why matter persists. At particle colliders such as CERN's Large Hadron Collider, scientists smash protons at energies mimicking the Big Bang's heat, searching for undiscovered particles or forces, perhaps a new form of asymmetry beyond the weak force. The 2012 discovery of the Higgs boson, a particle tied to mass itself, was a triumph, yet questions linger, with future upgrades aiming for 27 TeV collisions by the 2030s to probe deeper. Let's pause and reflect. Does the idea of uncovering these hidden rules through human ingenuity fill you with awe, knowing each experiment brings us closer to understanding our cosmic roots? This quest ties into exoplanet mysteries, as the laws we seek shaped not just Earth but every potential world. Over 5,000 confirmed by 2023 via NASA's TESS mission, each a canvas of matter's ancient victory. Technology like the upcoming Vera C. Rubin Observatory, starting in 2025, will map billions of galaxies, searching for patterns in cosmic structure that might hint at primordial asymmetries. As we linger on this thought, consider how these searches connect to our broader place in the cosmos, reminding us of Earth's fragility and wonder. A planet of 12,742 kilometers diameter, orbiting at just the right distance for life, a product of rules we're only beginning to grasp. Let's transition now to the philosophical heart of symmetry and imperfection, weaving these scientific endeavors into what they mean for our sense of belonging in this vast universe. This exploration roots in planetary science facts, grounding us in the reality that Earth's habitability, with its precise 23.5-degree axial tilt, owes everything to matter's survival. So let's drift forward, wrapped in the gentle glow of human curiosity, marveling at how each discovery, from waves in spacetime to particles in tunnels, illuminates the balance and breaks that define our cosmic home, urging us to keep seeking amid the endless stars. Let's rest in the profound interplay of symmetry and imperfection, reflecting on what these cosmic principles mean for our place in the universe. Picture Earth as a tiny, shimmering orb suspended in the infinite dark, a world born from a universe that could have been nothing but light, a testament to matter's quiet victory over antimatter through broken symmetries. Symmetry, as we've seen, is nature's blueprint, from the spiral of a galaxy to the laws of physics preserved by Emmy Noether's theorem. Yet it's the subtle cracks, the asymmetries in forces like the weak nuclear force, that allowed a sliver of matter to endure, crafting stars, planets, and life over 13.8 billion years. Imagine the cosmos as a vast garden, where symmetry plants the seeds of order, but imperfection waters them into unique blooms. Earth, with its oceans and forests, being one such flower. This balance of perfection and flaw mirrors our own existence. Aren't we, too, a blend of harmony and quirks, shaped by the same cosmic story? Let's pause and breathe in this thought. Does knowing our world emerged from such a delicate imbalance make you feel more connected to the stars, more in awe of life's rarity? This ties into cosmic wonder and exoplanet mysteries, as we ponder if other worlds, perhaps among the thousands charted by missions like Kepler, share this fragile origin, each a potential sibling in the family of matter-made realms. Planetary science facts ground us here. Earth, orbiting at 149.6 million kilometers from a star that's one of 100 billion in the Milky Way, thrives due to conditions set by ancient asymmetries, a reminder of our unique yet shared cosmic heritage. As we reflect, let's marvel at humanity's quest to uncover these hidden rules, from LIGO's gravitational wave detections since 2015 to CERN's particle collisions at 13 TeV, each step revealing more about the universe's quiet mathematics. What does this mean for us? It's a call to cherish our fleeting moment in this vast expanse, to see Earth not just as home but as a miracle of broken balance, inspiring us to protect its fragile beauty. I invite you to sit with this wonder. Close your eyes for a moment and imagine the universe's first light, the first fracture of symmetry leading to you here now. If this gentle exploration into the cosmos has touched your heart or sparked your curiosity, I'd be honored if you'd give this video a like. Subscribe to Earth with Nature for more serene journeys through science, space, and time, and share your thoughts in the comments below. What does the universe's delicate dance of symmetry and imperfection mean to you? Does it deepen your sense of belonging or ignite new questions about our place among the stars? Let's keep this conversation alive, nurturing our shared awe for the mysteries of creation. Thank you for joining me on this soothing voyage into cosmic wonder. Until next time, look up at the night sky, feel the weight of ancient stories, and remember, you are part of this grand, imperfect, beautiful universe. Let's continue exploring together, wrapped in the endless curiosity that connects us to everything that is.